what I'm going to talk about is I'm going to talk about a little bit about definitions, and then we'll go through some classical constructions and proofs. What I'm going to do is I'm going to introduce the topic of secure two-party computation. And I'm not sure, actually, in the end, if anyone of the lecturers after me is going to talk specifically about secure two-party computation, although I think at least one speaker is going to talk about oblivious transfer. But I'll then use that as a way to define the properties of zero knowledge and proofs of knowledge. So in the general setting of secure, and I'll look here at the case of two-party computation, what we have two parties. Let me just call them, P1 and P2 for now. P1 holding an input x and P2 holding an input y. And what they want to do is they want to be able to run some protocol, some interactive protocol with each other. Okay, you can see already this is a kind of a very different setting from the kinds of things we talked about this morning with encryption and signatures, and I'll even comment about that further in a moment. And let's assume that at the end of this interaction, the goal here is for one of the parties, let's just say P2, to output some function of both of the parties' inputs. So here, the goal is for P2 to output some function fxy. So you can think of any function you like, but maybe if you want to be concrete, you can think about parties interacting and they want to learn which of their inputs is the larger of the two. Okay, so maybe fxy is outputting the predicate of whether or not x is greater than or equal to y. And in general, they'd like to do this kind of an interaction. Well, so first of all, we have some kind of a correctness property, right, that says if they both run the protocol honestly, then at the end of the interaction, P2 will indeed hold the correct value fxy. Okay, that's fine. What we'd like to think about is what we might want from the point of view of security. And at an informal level, there are a couple things we might think about. So one thing we might want is privacy. What would privacy mean in this example? Well, it would mean, in particular, that after this interaction, P1 should learn nothing about the input of P2. Okay, that's possible here because P1 gets no output in the protocol. Even though there are messages exchanged, we might be able to set things up such that P1 learns nothing about P2's input. And on the flip side, what we'd like is for P2 to not learn anything about P1's input. But of course, it's not quite possible because P2 learns, in particular, the output of the function fxy. And in the example I gave, fxy was a bit, but more generally, it could be a multi-bit output. And so there could potentially be quite a lot of information that's leaked about x to P2. But what we'd like is that the only thing that P2 learns about x is the evaluation of f on the unknown input x and P2's known input and chosen input y. Other properties we might want are something like a correctness property, saying that the output fxy that P2 receives should correspond to some input x held by P1, and it shouldn't be possible for P1 to cause the output learned by P2 to be something that could never possibly arise as the evaluation of x on some pair of inputs, and actually on some input plus the known input of P2. There are other less obvious properties. So for example, we might want it to be impossible for P1 to be able to force its input to be the same as P2's input, right? That's not a violation of correctness per se, but it's kind of a violation of what we might call input independence. So because it seems wrong for P1 to be able to do that. And there might be other things as well. And it's difficult really to enumerate and to think about and even to define all these different properties we might want one by one. So what we're going to do instead is we're going to look at what we might want in an ideal world, what we might want from an ideal world evaluation of or an ideal world execution where P2 learns fxy and nothing else. And then we're going to define security by comparing the real world execution of some protocol to what we see in that ideal world. So what would the ideal world look like in this case? So the ideal world would look like we have P1 with input x like before, we have P2 with input y like before. And in an ideal world, these parties would have available to them a trusted external party who agrees to compute f on their behalf. And so what would happen in this ideal world execution? Well, P1 would send its input to f. Okay? An honest P1 will send X, but a malicious or dishonest P1 can maybe change its input to whatever it likes. But let's say in this picture, well, let me actually I'll write X prime. P2 can decide what value Y prime to send. Regardless of what values those parties send, this trusted external functionality will evaluate the function f, the agreed upon function f, on the two inputs and return the output value f x prime, y prime to P2. Okay? So there's no protocol here. There's just two parties having access to an external trusted helper. And you can see that all the properties we talked about before hold here as well, right? So P1 learns nothing about P2's input y, because P1 is learning no information at all. It's just sending a value to the functionality, and that's it. P2 is learning nothing about x other than the value of f x y prime. Correctness holds in the sense that no matter what value P1 sends to the functionality, it is computing f on some input, and so the value that P2 outputs is going to correspond to the evaluation of f on some input. Input independence holds because P1 has to send a value to the box, to the functionality, independent of whatever value P2 sends to the functionality. And so you can see that this is really encapsulating all those properties we talked about a minute ago, plus potentially other things that we might care about as well, that I haven't explicitly talked about. So how can we compare the real-world execution of some protocol to this ideal world execution? Well, what we can do is we can look at distributions in the ideal world and compare them to certain distributions in the ideal world. So what we can do is we can define, I'm going to do this a little bit informally because if I write down all the details, it's going to be too much here. But we can define some kind of an ideal world execution involving the evaluation of a function f, and let's say also involving some adversary A. So this adversary A, we're going to imagine here, can decide in advance to corrupt either P1 or P2. Okay? So A makes a decision before anything happens to corrupt either P1 or P2. And just to make it explicit, so if A corrupts P1, then what's going to happen is that A gets to view the input x of P1. Then it can decide if it likes to change it to some value x prime that it sends to the functionality. The honest party, so P2 in that example, is always going to send its actual input to the party. So in that case, y prime would be equal to y because P2 is honest. Okay, but the corrupted party can change its value. So we can look at a distribution, ideal FA, when the initial inputs of the parties are x and y. And what this is going to be, it's going to be basically the view of the corrupted party. Let's call it the view of A. Along with the output, I'll just write H for the honest party. Okay? So what this means is that if, again, I'll work with the example where A corrupts P1. So A corrupts P1. Let me step back a minute. The parties are given inputs x, y. A decides to corrupt P1. It sees x. It can then decide to change that value to some other value x prime. It sends that value to the functionality. The honest party P2 in this example is going to send its input y to the trusted functionality. It receives in return the value f x prime y from that functionality, and that's the value that P2 outputs because P2 is honest in this particular example. Okay, the honest party outputs the value it receives from the functionality. And then the view in this case of the corrupted party, which in this example was P1, is really, in this example, nothing because it didn't receive anything from the functionality. If the corrupted party were P2, then its view would consist of the output that it received also from the trusted functionality. I guess, yeah, more generally, you might have different inputs going to the two different parties. Here, I'm just considering a special case where only one party receives output. We can correspondingly define a distribution real pi A, where pi is some interactive protocol being run between the two parties that corresponds to the initial picture that I wrote. And here, we're going to allow the adversary to output an arbitrary function. Oh, I'm sorry. I made a little mistake here. Let me do this. I'm going to allow A there to output an arbitrary function of its view. Here I want for simplicity, just the party to output its view itself, and the output of the honest party, which is its output from the protocol. Okay? So let me just go back to this example here. So again, if we think of P1 as a corrupted party, and we think of pi, some protocol pi being fixed that the parties are going to be running in advance, so the attacker who corrupts P1 gets to see X, and then it starts running an interaction with an honest party, in this case, running protocol pi on input Y. Now, of course, one thing the attacker can do is simply run the protocol honestly on some alternate input X prime. But more generally, it can do other things as well. It could choose to deviate from the protocol in some way if that gives it some advantage. At the end of the execution, that party, the corrupted party P1 in this example, has some view of its interaction, which in this case would consist at least of the messages that it receives from P2. P2 receives some output as dictated by the protocol, right, which is supposed to be fxy, but in general might be something different, especially if the adversary deviated. And whatever P2 outputs at the end of this interaction, that's going to be the value in this notation below here. Okay? Good. And what we'll say is that a protocol, pi, is secure if for all, let's say, efficient, meaning like probabilistic polynomial time, okay, and all x, y, and z, where x and y are going to correspond to the inputs of the parties, z will represent some auxiliary information that A might have, whether about the honest party's input or whether about something else going on. It just represents some auxiliary information. Sorry, I'm probably messing up order of quantifiers here. So there exists another adversary I'll call S here, and we'll see why in a minute, such that for all x, y, and z, okay, the ideal execution involving the adversary with auxiliary information z and the honest parties, or the parties rather, starting out with inputs x and y, should be computationally indistinguishable from a real execution. Oh, I messed this up again. So Dominique, you should catch me if I make mistakes, because I know you're good at that. Let me start over a minute. So we want to compare rather the real execution involving A okay? And what we want to say is that for any adversary attacking the real-world protocol, there should exist an adversary S running in the ideal world execution such that the random variables I defined above are computationally indistinguishable from the view in the real world. Okay? So let me just, and I didn't explicitly talk about computational indistinguishability in the last lecture, but this is kind of very similar to when I defined pseudo-randomness, and I talked about for pseudo-randomness that the property defining what that means is that it's hard for a computationally bounded attacker to distinguish whether it's being given a sample from the output of the pseudo-random generator or the output of a truly uniform distribution. So here, too, basically the idea is that it should be hard for a computationally bounded distinguisher to tell whether it's given the output of a real-world execution, where by output here I mean what I have written up here, or whether what it's given corresponds to the ideal world execution. Okay? So why does this kind of give us what we want? Well, if you think about it, this implies in particular that the real-world execution of the protocol should not leak information about one of the party's inputs. So let's go with this running example where P1 is the party that gets corrupted. So if there were a way to deduce information about P2's input Y from the interaction of the protocol, then we could have an adversary who learned, let's just say, for example, that there was an adversary P1 who could interact in the protocol and learn P2's input in its entirety, okay, from their view. Well, then the distribution here corresponding to the real-world execution, the view, the messages that it received from P2 would contain information that would allow somebody to determine the value y of the second party. Okay? But in the ideal world execution, there's clearly no way for that to happen. In the ideal world execution, the adversary A is being forced to generate some output based only on its interaction with the ideal functionality. But the interaction of P1 with the ideal functionality consists only of sending its input and getting nothing back. So there's basically would be no way then for the ideal world execution to be indistinguishable from the real world execution if the real world execution actually leaked information. Okay? It's a little bit hand-wavy because I didn't fully define what I mean by indistinguishability here, but like I said, doing that would take up another 10 minutes or so. But at least intuitively, the idea is that what we want to do is we want to show how to convert any real-world adversary A into a corresponding ideal-world adversary S. And the reason I call it S is because we're going to talk about it and think about it as what's called a simulator, such that the executions of the two you can think of as being indistinguishable from each other. Another way of saying it is that whatever an attacker could do, whatever behavior an attacker could cause in a real-world execution of protocol pi, there's an equivalent attacker S that can cause the same effect in the ideal world execution. And since the ideal world execution is secure by definition, right, because of the way we set up the ideal world, that tells you that the real world execution is secure as well. Yes? The view of A, right, so the question is about the view of A. So the view of A is the transcript, but it's also, can be, it's the input of the party that it corrupted. It's also maybe its randomness if it has any randomness. It's also this value Z that represents other information it might have. But yeah, anything that's in the view of the adversary when attacking the protocol is part of that random variable. Yeah, no, it's a good question because I maybe went over it too quickly. So yeah, so this I don't know. I don't want to redefine the notation now, but basically in this ideal world, so this output of the honest party corresponds to what it receives from the ideal functionality. This output of A is an arbitrary function of whatever its view is in the ideal world. So here, the view in the ideal world is kind of nothing interesting because it's not receiving anything, so it just means it can output whatever it likes. Yeah, so that's what I mean there. So in particular, what's going to happen, in a moment is that we're going to, when we want to show that this definition holds for some protocol, we're going to need, in particular, to come up with some simulator S that's going to start generating something that looks like a transcript. So yeah, that's exactly what's going to happen. And no question is silly. Right? So, other questions? Okay, so rather than talk about general secure two-party computation, what I want to do is I want to look at a particular function of interest that's going to then carry us through for the rest of the lecture. And let's see, I guess, let me do a little bit of a review here. So I don't know how many people are familiar with this because it's actually not something that I put up as one of the prerequisites. But we have this concept in computer science. Let me actually not define it in full generality here. Let me define this notion of a relation. So a relation R is simply a pair of values. Okay? So if you have some pair of values, they're either in this relation or they're not in this relation. We can define a language based on this relation, which is just going to be a set of instances X, such that there exists a W such that XW is in R. Okay? So for people who are familiar with this, but I know that maybe not everyone in the room is, this basically, if I require that checking membership in R is efficient, then this basically corresponds to a definition of the class NP. Okay? So we're looking, what I'm going to define is like this notion of, I'm going to call X an instance, I'm going to call W a witness. We have this relation defined by certain pairs of instances and their corresponding witnesses. And then we can define, based on that, a language, which is the set of instances for which there exists a valid witness with respect to this relation R. I'll give a concrete example in a minute, so if you're lost in this notation, don't worry, we'll come back to a concrete example in a moment. But what I want to consider here is a particular case of a function where even one of the parties, well, let's see, we'll have a party P1, which I'm now just going to call P, because it's going to correspond to what I'll call a prover. And I'm going to call the second party V for verifier. The input of V is going to be some instance X. The input of P is going to be some pair X and W. And the function that they're going to compute, this is in the ideal world, is basically evaluating this relation R. So this is, again, one of these things where if I want to be fully formal, it'll be a little bit of a mess. But I'll try to be a little bit formal here. Okay, so first of all, what this functionality is going to do, it's going to just do a sanity check and make sure that the x's are equal. And if they're not equal, it will just return maybe some error to V, or return, maybe let's just make it return 0 to V in that case. But the interesting case is going to be when the x's are equal. And in that case, what this functionality is going to do, it's going to simply check whether that pair xw is in the relation R. So I'm just going to overload notation and let R also denote the algorithm for determining whether or not that's true. And then it's going to return the corresponding value to V. So it's going to return R xw, which again is equivalent to asking whether the pair xw is in the set R if the pair xw satisfies the relation. Okay? Let's look actually just at a concrete example like I promised. And again, for those of you who have seen NP and NP completeness, this may be familiar. For those of you who haven't, you can just consider this as kind of an abstract problem. But we can look at the problem of graph Hamiltonicity. So what we have here is we have a graph. Well, the question is, you're given, well, let's say that X corresponds to a graph on n vertices. And W will correspond to, let me do it this way. I'm going to define this language Hamiltonicity, which will be the set of graphs X such that exists a Hamiltonian cycle in the graph X. What does it mean to have a Hamiltonian cycle? It means that you have a sequence of edges that you can follow that will traverse each vertex in the graph exactly once, and then return back to its starting position. Okay, so like if I just give us a small example here, right? Something like that. So this graph here should have a Hamiltonian cycle because I can, let's see if I use a different color. I can follow. Oh, it doesn't have a cycle actually. Okay, I messed up. Well, okay, this graph is an example of not having a Hamiltonian cycle. But if you have, if I wanted to be, to do it, I could just draw a cycle graph. But yeah, so basically, you have a Hamiltonian cycle if you have a sequence of edges such that you traverse every vertex once and then end up back at your starting point. So the relation in this case, right, would be a graph along with the sequence of vertices to traverse that would form a Hamiltonian cycle. Right? If I give you the graph, which includes all the vertices and all the edges, and then I list out in order, right, the vertices that you're supposed to traverse that constitute a Hamiltonian cycle, it's possible to verify that what's presented, the witness which is presented, namely that sequence of vertices, is actually a valid Hamiltonian cycle. How would you do that? Well, you would first of all check that every vertex in the graph appears in that list exactly once. And then you would check that for every adjacent pair of vertices in that list, there is in fact an edge between them, and then also at the end that you can wrap around back to the beginning. Okay, so you can check one by one down the list to make sure that there is indeed an edge between each pair of adjacent vertices, and so you can efficiently check whether or not a given sequence of vertices constitutes a Hamiltonian cycle in a given graph. right? And some graphs, may have no Hamiltonian cycles, in which case they wouldn't be in this language, and in which case no sequence of vertices would satisfy that check. Other graphs may have one or even multiple Hamiltonian cycles. It's fine if you have more than one. We're only asking about existence of at least one Hamiltonian cycle in the graph. Okay? So in this particular example, returning to what's going on in the ideal world, what we would have is we would have the prover and verifier both holding identical copies of some graph that here I'm calling X. The prover would additionally have a witness verifying the fact that that graph does indeed have a Hamiltonian cycle. And the prover wants to convince the verifier of that fact. The prover wants to convince the verifier that there is indeed a Hamiltonian cycle in that graph. Now, of course, an easy way to do that would be to have the prover just simply send the Hamiltonian cycle to the verifier. But that reveals a lot more information than simply the fact that a Hamiltonian cycle exists. So in this ideal world execution, the only thing that V learns is a bit indicating whether or not P holds a valid witness for the fact that there's a Hamiltonian cycle, right? So of course, well, let's just think about it. If V gets a bit 1 from the ideal functionality, then that doesn't reveal anything about which witness the prover has, and doesn't reveal anything about any information about that witness. But it does reveal the fact that there is a valid witness that the graph X contains a Hamiltonian cycle, and therefore it does reveal the fact that this graph has a Hamiltonian cycle, right? Because again, in the ideal world, the functionality never produces the wrong output, and so if it sends a bit 1 to the verifier, then there must have been some W, some valid W, that the prover sent to R to make it spit back 1 to the verifier. Okay? So I'll just kind of comment here, because I keep on thinking about it in the back of my head. So if you were going to try to prove anything about some protocol realizing this functionality, you kind of would technically have to consider these different possibilities. Like, for example, you'd have to consider the possibility that P would send some garbage value to R, or maybe send X prime not equal to X, but in any event, making the functionality return 0 to V. But that's kind of not an interesting case, so I'm not going to talk about it. I'm just going to really be focusing on the case where P sends something that makes the functionality return 1 to V. Okay, questions so far? Okay, so based on this framework and based on what we talked about already about defining secure two-party computation, we can define two very useful notions that, like I said, I'm going to spend the rest of the time talking about, which are zero knowledge and proofs of knowledge. And what I would say is that if we have some protocol pi, yes? Yes. So it's more of a little bit of a technicality because, I mean, what I want to do basically is I want to prevent P from like changing X to some other X prime. And the way to do that is by having V send X and then R just checking that they're equal as a sanity check. I mean, there are other ways you can do it as well. Maybe another way to do it, another way to do it would be just to not have P send X at all, and just have R evaluate on the X from the V and the W from P. Yeah, you could do that too, that's fine. Yeah, you could do that too. That simplifies things a little bit. Maybe that's a fine way to do it too. Yeah. Good. Other questions? So good. So if we fix some protocol pi, what I'll say, and let me just say a minute, so at least pi should be correct, meaning that if the prover and verifier are both honest, then they should interact. At the end of the execution, V should output 1. If indeed P is running on a valid witness W for the graph X. But what I'll say here is that a protocol pi is a zero knowledge protocol. And I'll abbreviate this by ZK. If it's secure against a malicious verifier. Okay, what do I mean by secure? I mean, going back to this definition I had a moment ago for secure computation, but restricting attention now to adversaries A that always corrupt the verifier. Okay? So just thinking about it, because it'll be useful when we come to a particular example in a moment, that would mean that what we would need to show in order to prove a protocol zero knowledge is that for all efficient cheating verifiers, because now the adversary is corrupting the verifier. So for all efficient cheating verifiers, there should exist a simulator such that that simulator can output a view of the verifier. That simulator in the ideal world is able to output something that's indistinguishable from the view of the verifier in the real-world interaction. Okay, so think about some distribution over messages that the verifier receives via an interaction of this protocol pi. And we're going to want that there should exist a simulator in the ideal world, right, where the only information available to that simulator in the ideal world is the instance x, and then the single bit telling it that, yes, indeed, there does exist a valid witness for that x. And based on that information alone, it should be able to concoct a view or a transcript that looks indistinguishable from the transcript of the execution of the protocol in the real world. Okay? And this is basically the zero-knowledge property. Well, that is the zero-knowledge property. And then the second property is what I'll call a proof of knowledge. That I'll abbreviate by POK. And this is going to handle security, secure against a malicious prover. Now I'm going to just jump ahead a little bit and just kind of, again, think about what that's going to mean. So again, security means in this, according to this definition of secure two-party computation that I gave. But let's think again about what it means in this case. So what does it mean for a cheating prover, right? For a cheating prover, there's nothing really, it's not going to be difficult for us to simulate maybe the view of the prover. But the interesting thing here is to simulate the output bit of the verifier. Right? Because think about what's going on in the ideal world. In the ideal world execution, in the real world execution, let's assume we have some cheating prover who's able to make the verifier accept, meaning make the verifier output 1. So then there has to be a corresponding simulator in the ideal world that can also make the honest verifier output 1. But the honest verifier in the ideal world is going to output whatever it gets sent by the ideal functionality. And the ideal functionality is only going to send a 1 if it receives a valid witness, W, from the prover. And so the prover has to be, the simulator in the ideal world has to be able to somehow generate, right, from the cheating prover, it's going to have to be able to extract some valid witness W for the fact that the graph accepts, in the case when that cheating prover is able to make the verifier accept in the real world. Okay? It'll make more sense, I think, when we come to some concrete protocol. I'm anyway first going to do zero knowledge and then come back to the proof of knowledge property. But essentially what I wanted to get across here is the fact that both zero knowledge and the proof of knowledge property can really be viewed as kind of two different cases of security from the context of general secure two-party computation. Good. So let's look actually at a concrete protocol, and we'll look at proving security. We'll look at the case of proving exactly this case of Hamiltonicity. So I need to first introduce one other building block, which is commitment schemes. And I think this I'm also going to do kind of a little bit informally, because again, doing it completely formally would take a bit of time. The basic idea of a commitment scheme, question? Yes, correct. Right. And is there a way to secure the proof of knowledge? Yeah, so, okay, good, right. So the question is more about like an intuitive description of what's going on here. So yeah, so the zero knowledge property would tell you that after an interaction of this protocol pi, the verifier learns, so let's stick with the case of Hamiltonian cycle. The verifier learns that some particular graph has a Hamiltonian cycle, but doesn't learn any additional information beyond that. Okay, it doesn't learn anything about the Hamiltonian cycle itself. The proof of knowledge property, it's a little bit funny, but basically what it tells you is that if a prover is able to convince a verifier to output 1 in this execution of the protocol, then the prover does indeed know a witness that the graph has a Hamiltonian cycle. What does it mean technically to say that the prover knows a witness. What it means is that we can interact with that prover and actually extract that witness from it. Namely, we can interact with the prover, and at the end of that interaction, we're going to be able to explicitly write down what a witness is. We're going to explicitly be able to write down a witness for the fact that the graph is Hamiltonian.
Doesn't mean you cannot have both properties at the same time.
Great question. So the question is whether we can have both properties at the same time. So the answer is you can have both properties at the same time. It is interesting, and I probably won't have time to get to it today. Maybe I'll touch on it at the end. You'll see that there's like some conflicting requirements a little bit on the two sides. If you want to prove one, it's a little hard to prove the other, and vice versa. You have to work at it a little bit, but you can definitely achieve both, and I'll show actually a protocol achieving both. You know, doing it in constant rounds is a little bit harder, but yeah, but I'm not going to care about round complexity. But yeah, you can achieve both, yes. I mean, I should have said actually that, you know, I should have given everything away by saying that we have these general completeness results that tell us that you can do secure two-party computation for arbitrary functions. So once you have that, then it follows as a corollary, but obviously there's a lot of, you know, interesting stuff besides the corollary. Yes?
In the proof of knowledge case, I understand the view of the simulator, what you're talking about, but when you talk about the specific Hamiltonian cycle problem, and you're talking about the simulator participating in the ideal protocol, where you have this third trusted party computing the output, are you already sort of implying something about the result here, when you're saying that the only way that you can affect that is with a valid W?
Yeah. So what I'm saying is that, right. So you could have an adversarial prover that sends garbage to R and then makes V output 0. And technically speaking, you have to handle that case as well, but it's not really a very interesting case because it's easy to handle that case. The interesting case is when you have, well, the interesting case is in the real world where you have some prover, some cheating prover, who's able to make the verifier output 1. And then if you want to be able to simulate that in the ideal world, you're going to have to come up with something that's going to send a valid witness to R, because that's the only way it's going to send a 1 to the honest party. Does that kind of answer your question?
Yeah.
Okay. Good. So I think I'm going to leave this, you know, very high level, but the basic idea of a commitment scheme is that it's going to be a two-phase protocol that allows a sender to commit to, let's just say, a single bit. So let me just write it out here. So we're going to have two phases here. We're going to have a sender and a receiver. In phase 1, the sender is going to send some information to the receiver. It could possibly be an interactive protocol. I'm just writing it here as a non-interactive protocol for simplicity. And that's the end of phase 1. And then during phase 2, the sender will send some information to R that will allow R to recover some bit B. And the properties that we want here are called hiding and binding. The hiding property, roughly speaking, says that after the first phase of the protocol, right, so before this dotted line, R has no information about the bit B that the sender committed to. And the binding property is that at the end of the first phase, the sender can only possibly open up its commitment to a single bit B. Okay? So the point is that you can think about this as the sender putting a bit B inside of an envelope and then giving that envelope to the receiver, or maybe a lockbox is a better idea. And then in the second phase, sending over a key that allows the receiver to open up that lockbox, right? So the bit that's inside the locked box is completely hidden from the receiver at the end of the first phase, but the sender is committed to some particular bit at the end of the first phase because there's no way it can go and change what's physically inside the box after it's handed the box over. And basically, a cryptographic commitment scheme allows us to instantiate that idea of a lockbox using some cryptographic protocol. If you like, you can think about, well, maybe I don't want you to think about it. Just think about the fact that these things exist. And yeah, let's just take them as a black box. I'll draw them even as envelopes or boxes. So you don't even have to think about how we realize these. But you can realize them based on standard cryptographic assumptions. Okay? And what I want to show now is a protocol based on a commitment scheme that will allow a prover to convince a verifier that some graph is indeed Hamiltonian. Okay, so what's the setup here? We have some, again, our prover. The prover has a graph. Let me just call the graph G now, switch to that. And it has a Hamiltonian cycle. I'll call W. And we have a verifier who has a copy of the same graph. Okay? So the protocol that I'm going to describe is going to consist of a number of iterations of a basic subroutine. And that basic subroutine is going to work in the following way. What the prover is going to do is it's going to randomly permute the graph G. So what I mean by that is basically do a random relabeling of the vertices. And then it's going to commit bitwise to the adjacency matrix of that permuted graph. So if G has n vertices, that means we're sending a total of n squared commitments. I'm just arranging them in this matrix form, right? So it's defining, right, permuting this graph G is giving us a new adjacency matrix corresponding to the permuted graph, call it G prime, and then the prover is committing entry by entry to the adjacency matrix of that graph. What the verifier is then going to do is choose a random bit. And then send that bit back to the prover. And then there are two possibilities, right? The challenge bit is either 0 or 1. So if b equals 0, what we're going to do is we're going to have the prover open all commitments. And it can also reveal the permutation that it used to generate this permuted copy of the graph G prime. And if b equals 1, then what it's going to do is going to open all the commitments. Well, not all the commitments in the graph, but all the commitments in a Hamiltonian cycle. Okay, so what would that mean exactly? Well, that would mean that if the Hamiltonian cycle, right, if there's a Hamiltonian cycle in G, then there's also a Hamiltonian cycle in the permuted graph. And what that would mean is that if the Hamiltonian cycle, for example, went from vertex 1 to 3 to 10, and then back to 1 again, or whatever. So then what I would do is I would open the element in the adjacency matrix showing that there's an edge from 1 to 3, right? So I open position 1, 3 of the adjacency matrix, and V would confirm that there's a 1 there, indicating the presence of an edge. And then I would also open, right, what did I say, 1, 3, 10? So then I would also open position 3, 10 of the adjacency matrix and allow the verifier to be convinced that there was a 1 there, indicating the presence of an edge from 3 to 10, and then so on all the way around until it verifies that there's an edge going back from the final vertex back to the original node where I started. Okay? So in that particular example, I would be opening up I guess, n different commitments in the graph. And so in either case, I generate my response accordingly. Okay? And then the verifier needs to check, right? So let's just go through and make sure we understand what that means. So if b equals 0, then what the verifier has to check is, first of all, that all the commitments in the adjacency matrix were indeed opened correctly. And then along with the openings of those commitments, the prover would also be revealing a permutation showing how it got from the original graph G to this permuted copy of the graph G prime. And the verifier just goes ahead and checks edge by edge that the permutation does indeed, is faithful in terms of the edge mappings between the two graphs. Okay, we only need to send that, we need to send that permutation because solving graph isomorphism is hard, and so, we want to make it easy for the prover to verify. And in the second case, we already talked about it. What that means is that the verifier gets a set of n decommitments, n openings of those commitments. It needs to verify that those are all correct openings. And then it needs to verify that, that everything is structured correctly, right? That every vertex appears in the sequence, and that there's always an edge, namely a 1 in the adjacency matrix between consecutive pairs of vertices. Okay? Now, just thinking about this before I prove anything about it, right? Why is this convincing at all to the verifier? Okay? Well, it's convincing to the verifier for the following reason. So what I claim is that it's impossible for a prover to convince a verifier to accept with probability 1 unless the graph has a Hamiltonian cycle. Okay? Why is that the case? Because if the prover can convince the verifier with probability 1, then what that means is that it's able to send some set of commitments in the first round, such that regardless of whether the verifier responds with a 0 or a 1, the prover will be able to open correctly. So what that means is that if the prover responds with a 0, if the verifier sends back a 0, then the prover can open up all the commitments and it will indeed be a permuted copy of the original graph. And if the verifier sends back a 1, then the prover is going to open some subset of those elements in the adjacency matrix, verifying that there is indeed a Hamiltonian cycle there. And moreover, the binding property of the commitment scheme will imply that any edge that was present when the challenge was 1 was also present when the challenge was 0, and vice versa, right? That's exactly where we're using the binding property of the commitment scheme. And so the Hamiltonian cycle that was demonstrated when b equals 1 is going to exactly map to a Hamiltonian cycle in a permuted graph when b is 0. And that is going to map back to the original graph via the permutation that the prover has to reveal as well. Okay? Now, having said that, right, it is possible here for the prover to cheat with probability half. Right? The prover can cheat with probability half by simply guessing in advance what the verifier's challenge is going to be. So let's assume that the graph does not have a Hamiltonian cycle, or the prover doesn't know one if there is one. So if the prover guesses that the verifier's challenge is going to be a 0, well, it'll just commute to a permuted copy of the graph, no problem, and then when it gets challenge 0, it can open everything up and everything's fine. Or it can guess that the verifier's challenge is going to be a 1, and in that case, what the prover will do is simply commit to the adjacency matrix for a random Hamiltonian cycle. Okay? And in each case, it will not be able to open up the commitments properly for the other query, for the other challenge, in case it was wrong. But if its guess was correct, which will be true with probability half, it will be able to answer correctly. Okay? So the prover here can cheat with probability half, but can't cheat with probability 1. Now we can address that by taking this protocol, this 3-round protocol, and running it sequentially n times. And that will allow us to reduce the soundness error from 1/2 to 1/2 to the n. Okay? And that will be much more convincing then to the verifier. Obviously, it depends how high n is, but that will be much more convincing to the verifier that if the prover is able to successfully convince the verifier in all n of those interactions, then the verifier really should be convinced that the prover has a valid witness for this commitment, for this graph. Okay, so what I want to do is I want to take some of that intuition, I want to take some of that intuition and I want to now look at, I'm going to give a formal proof of that, but I want to also just look quickly at the zero knowledge property, right? Why does this reveal nothing to the verifier? And I'm going to prove it more formally in a minute. But why does it reveal nothing to the verifier? Because from the point of view of the verifier, right, the verifier can basically choose to send back a 0 or a 1. But it knows what answer it's going to get in either case, right? If it sends back a 0, it knows it's going to see a random permuted copy of the original graph. And if it sends a 1, it knows it's going to get back the opening of a random permutation of a Hamiltonian cycle, a random cycle. Okay? So essentially, modulo the fact that we have these commitments here, the verifier is not really learning anything from the interaction. Right? The verifier can, again, basically predict the 3rd-round response from its 2nd-round challenge. And that's kind of the intuition for why this is a zero-knowledge protocol. So let's see if I have time to prove anything formally here. Let me see if I can prove the zero-knowledge property. So I claim that this protocol is zero-knowledge. Okay, what do we need in order to prove zero-knowledge? Remember, what we need is we need a way to show how we can simulate the view of any possibly cheating verifier, efficient verifier. So let's fix some verifier, some efficient verifier. I'll call it V star, right? It's malicious, so it doesn't have to follow the protocol honestly. And in particular, I mean, if we just look at this protocol, there's not actually very much that a verifier can do, because all it's doing is sending a single bit. But what it can do, that's a deviation from the protocol, is the following. In the real protocol, the verifier is supposed to choose the bit B at random. But what a cheating verifier can do is it can choose that bit as an arbitrary function of the commitment sent in the 1st round. Okay? So it doesn't seem like much, but this is actually something that causes problems in the proof. And anyway, it's an allowable strategy of a cheating verifier. So that's basically what this verifier might do. So we need to show how to simulate the view of that verifier. So we're going to construct a simulator, S, as follows. So S, first of all, is going to be given a copy of the graph G, because the cheating verifier V star has a copy of that graph, yes?
Wait, so you're saying that a cheating verifier rather than a random one?
It can pick B non-randomly, yes.
Okay, and that's what would make it like a cheating verifier?
Right. So it's not only that it can pick it non-uniformly, but it can also pick it as some deterministic function of the first round message in particular. So it doesn't have to pick it like 60% 1, 40% 0. It can compute a hash function of the first message and then send that as the challenge. And in general, we don't even know how it's computing the challenge, but it can compute it in some arbitrary way. So what we're going to do is we're again going to use this idea of running the adversary here, the V star, as a subroutine. Okay, we do have access to it as a subroutine. We don't know how it works internally, but we can again interact with it. We know the input-output behavior, or the interface rather, of that adversary. So what we're going to do is the following for I equals 1 to n. We're going to choose a uniform B. Let me call it B star. So let me just say what I'm going to do here. I'm going to have the simulator repeatedly try the following strategy. It's going to basically do what I said earlier. What it's going to do is it's going to choose a random value B star, a random bit B star, and then it's going to proceed. Basically, it's going to make a guess that the verifier's next response is going to be B star. Okay? So we saw before, or we went through before, how if the prover knew in advance what the verifier's challenge was going to be, then the prover would be able to cheat. Right? So just to remind you of that, if we knew in advance that the verifier's challenge was going to be a 0, we would just send a permuted copy of the graph. And if we knew in advance that the verifier's challenge was going to be a 1, we would just send commitments to a random cycle. Okay? So we're going to do the same strategy here. So choose B star. We're going to generate commitments. Let me say that are consistent okay, and again, what I mean by consistent is just what I said, that if we guess that B star is 0, we're going to send commitments to a permuted copy of G. If we guess that B star is 1, we're going to send commitments to just a Hamiltonian cycle, right? A bunch of zeros and then a cycle of 1s. We run V star on those commitments. And when we run V star on those commitments, right, that's as if we're sending V star the first round message. And we get in return, right, its actual challenge bit B. Okay? Now there are two possibilities, right? Either B star is equal to B or it's not equal to B. If it's equal to B, then we're kind of golden, right? Because then we know exactly how to open up the commitments we started with to make it look like a completed accepting transaction. So if B star equals B, let me just say, we'll break. Right? So we're going to break out of this for loop, and then we'll be able to complete. Where am I here? Yeah. We'll be able to basically send the openings of those commitments as our third round message, and that will be our simulation. And if not, right, if B star is not equal to B, meaning that our guess was wrong, then we'll cycle back to the beginning and try again, another iteration of the for loop. Okay, so we're repeatedly trying to guess in advance what V star's response is going to be. And if we ever get it right, then we can continue the simulation. And only when we're wrong do we go back to the top of the iteration. So unfortunately, I'm running a little short on time. But let me say what the analysis, let me just finish writing this and then I'll do the analysis. don't know why this is happening. Okay, so if some iteration successful, finish simulation. Okay, by which I mean, again, that an iteration being successful means we correctly guessed the bit. Finishing the simulation means we just opened the commitments that we had consistent with the challenge bit that we got. So I'm not going to be able to do a full proof, unfortunately, but let me just sketch the highlights of the proof. Right? The main claims here are going to be that the probability that any particular iteration is successful is going to be roughly 1/2. So why is that the case? Well, basically because we're choosing our bit b star at random. And so regardless of what function v star is computing, we have probability 1/2 of getting that bit correctly. There's a little bit of a subtlety here, and that subtlety is because of the fact that, because of the commitments, essentially, that v star gets. If we treat those commitments as ideal, meaning that from the commitments, v star gets no information whatsoever about our bit b star that we chose, then in fact this probability would be exactly 1/2. If we have only computationally hiding commitments, then basically you have to do some argument there and prove that that because v star is computationally bounded, the probability that any particular iteration is successful is 1/2 plus or minus negligible. So overall then, right, the probability that at least one of these n iterations is successful is going to be 1 minus 2 to the minus n, or roughly 1 minus 2 to the minus n. And so with overwhelming probability, at least one of those iterations will be successful. And the second thing to show is that conditioned on a successful iteration, the transcript is indistinguishable from the real-world transcript. So again, right, they're not going to be identical, or let me say it differently. If the commitments were ideal, then the distributions would actually be identical, right? Because in condition on a successful iteration, we have exactly some challenge from the verifier and then some response to that challenge that exactly corresponds to what will be sent in the real world, or the distribution corresponds to what will be sent in the real world to make the verifier accept. Again, if we don't have ideal commitments, if we only have computationally hiding commitments, then we have to do an argument here, and we get only computational indistinguishability between the transcript that was output in the simulation and the real world transcript. Okay, but this gives you kind of a sense of the zero knowledge property. Let me say in the -1 minute I have remaining, just very quickly about the proof of knowledge property without writing anything. So for the proof of knowledge property, remember what we needed to show is that a prover that can make the verifier accept with high probability we can actually extract a witness from that prover. Think now about the simple case where we have a 3-round protocol, and all we want to say is that if the prover can convince the verifier with probability 1, then we can extract a witness. So we're going to do exactly what I said earlier, where I argued that if the prover could indeed respond correctly to both challenges, then it must know a witness. We're going to do that and make basically an algorithmic version of that. How is that algorithmic version going to work? What we're going to do is we're going to run one execution with the prover. We're going to get to the end, and if this prover indeed makes us accept with probability 1, we know that at the end of that execution, we will have the honest verifier would have output 1. We're then going to rewind the prover and send the complement of the bit that we sent in that original execution. If the prover is going to make the verifier accept with probability 1, then we know it will also respond correctly to that other challenge. And then we can use the 2 responses that we have from those 2 executions to exactly do what I said earlier. Namely, we look at the Hamiltonian cycle we got in response to the challenge bit 1. We line that up with the adjacency matrix that got fully opened when the challenge bit was 0. And then we map that back to the original graph by taking the inverse of the permutation that was also revealed when the challenge bit was 0 to recover a Hamiltonian cycle in the original graph. So the point here is just to show that what the argument I made earlier is actually can be made algorithmic and efficient as well. And just highlighting also the fact that we have the ability here to rewind the prover to some prior state in the execution of the protocol, and then send it a different challenge bit and see the response it would send in that case. And I didn't make it explicit actually, but in the proof of zero knowledge, we were making use of the same fact, right? We were making use of the fact that you can run V star multiple times, each time basically rewinding it or resetting it back to its original state and making it start the protocol over. And this is going to be a major source of challenge in the quantum setting, where if we take V star to be a quantum adversary, then you don't necessarily have the ability to rewind it in that way, because there are quantum mechanical operations that cannot be inverted, measurement in particular. Okay, so I apologize that I kind of ran short on time, but I'm happy to take other questions if there are any, or to discuss this further with anybody who's interested.